So I'm going to talk about something called equivocals when we do predictive modeling. I thought I'd finish these slides, and then I saw the about me's. So, statistician. I've worked in like the diagnostic industry, which I'll talk briefly about, pharmaceuticals, and I work at RStudio now doing mostly modeling packages, sort of in the order of the ones that I've released. I mean, they're all here, and a couple books. Not a hot dog, and yeah. That's my dog, who you can see the treats lying next to her, coming back from her walk, but she's, I think I was making like a hamburger, and that's the look I get. So anyway, all right, so I want to talk about some particular statistical methods you use in the diagnostic industry, and then how they might be applied in certain circumstances, not universally, but in certain circumstances when you're doing just general modeling. So, I had this job, and one of the jobs that I did was the algorithms for instruments, which means like you have like a really bad cough, and you go into the doctor, and you cough up a sputum sample, or they like tickle your throat. Sorry, Mar. You give them a sample, and then they put it in some diagnostic instrument, and it gets you a signal back. And the signal is, high probably if you have some, like, let's say tuberculosis, right? And low if you don't. And so you usually get data that looks like this, where the samples that are negatives have, a fairly low signal distribution, but a long tail. And then you have some positives here that on average are higher. And then, like, one of the final jobs a statistician would do in that case would be, what's my actual cutoff? Like, above what number here do I say somebody's an actual positive? And so typically you would use what's called an ROC curve, a receiver operating characteristic curve analysis. And, what that lets you do is balance, like, how many false negatives versus how many false positives and that kind of thing. And you might come up with a cutoff here, so the samples to the right of the negatives would be false positives, and your false negatives are down here. But what FDA would require us to do is put something in there called an equivocal zone, which means, like, if this cutoff is, let's say, 2.7, if you had a value of 2.71, they're like, yeah, maybe not a positive, even though it's past your cutoff. And so we had to do all this sensitivity analysis and things like that based on other data sets and come up with what they call an equivocal zone. And the equivocal zone in this particular instance would just be like a buffer around your cutoff that you determined with data that would optimize really the performance of the assay or the lab test. And we tried, you could make this performance really good by making it really wide. So we had to balance off, samples we exclude. So we had what we call reportable rate. Like, anything that's inside this equivocal zone, you would not actually report the value to the patient. You would say, hey, run the assay again or collect a new sample. It's so close, we don't think we can make a call between positive and negative. Okay, so we had to balance what we call the reportable rate, which is the number of patient samples that you actually give to people versus performance. Okay, and that was just something we had to do. And it seems like kind of like a dodgy thing if you're a statistician, because you're saying, hey, take the ones like you're most likely to miss and just get rid of those in your analysis. But at the very end, I have a link to an FDA guidance for that. So it's like a real thing that they would sort of make us do, whether we wanted to do or not. But again, these are the ones that you're most likely to miss. And you actually, when you do the analysis, you would get rid of any samples that are within the equivocal zone. Okay, so the idea is, especially when we're predicting something very important, there are situations where we might not want to make a prediction, right? We can take whatever data we have and funnel it through our model and get a number, but then we have to question, like, wait, should I give that number to somebody? Is there any criteria in which I shouldn't do that? And that's kind of what the previous equivocal zone was doing, is we think that these samples are problematic, not because of what their true answer is, but because of the value we're getting before we see the true answer, okay? So like an unsupervised rule that would make you exclude data you think are not good enough for predictions. And so, and this comes into play in these things called applicability domains. So I used to work a lot in computational chemistry, and this was really big there. Like, if you build, in pharma, a lot of times in drug discovery, we would build these models to make predictions on new potential drugs, right? What we call compounds. And these compounds a lot of times would be something that a chemist would design on their computer and would not actually exist, IRL. And then we would take those formulas that they come up with and make predictions on whether it's toxic or whether it's permeable, and all these things that chemists want to know, right? So if you have a model you built for, let's say, toxicity, and it involves like 1,000 data points, 1,000 compounds, and then you have a new compound that looks nothing like the ones that you've built your model on, you might flag that as not being applicable. Like, it's so different from the data that was used to build your model, you might not want to make a prediction on that, no matter what the actual value of the prediction is. Okay, and so these are situations, again, if you're predicting something like patient response, like you want to make sure you have a really definitive understanding of what the result should be from the model, maybe before you give that result to like a patient, because the consequences are potentially dire. So what I'm going to do is I'm going to show an example from drug discovery, and all you need to know about it is there's this thing called mutagenicity, which is when you take a drug and it actually, or you ingest anything really, and it damages your DNA, which I don't think I need to explain, it's like not a good thing, right? I mean, you won't grow like a second head or anything like that. Almost never. But mutagenicity is something we want to avoid. There's this thing called a lab test called the Ames test, and it gives you back like a yes or no answer. And so we have like a standard data set that we use that has about 4,300 data points. And then there's a lot of predictors. There's actually about 1,500 predictors, but they're mostly extremely correlated. And we have some ways of whittling that down to about 80 some predictors. So what we want to do is we want to build a model to make predictions on compounds as to whether they're toxic or not, this particular kind of toxicity. And then how could we use an equivocal zone to maybe filter out some predictions that we're not really quite sure about that we should give to the chemist. And in this particular case, like, it's hard to give bad news to people. And if you say, hey, I think there's like a 90% chance that your compound's going to like hurt somebody, they're very conscientious, but they're like, prove it. Right? So this is a situation where, like, if we called something equivocal, then what we would say is, hey, well, let's look at this particular structure and see if it's really related to existing structures or compounds that we know are dangerous and things like that. So what we would do in an equivocal situation here from a model would be tell the chemist to go back and just gather more data, or run it in a more definitive lab screen or something more to get better data, instead of accepting what this particular model would say. Okay, so what I'm going to do is I'm going to fit a logistic regression, which you probably are all familiar with, but I'm going to do a Bayesian logistic regression. And if you're not really familiar with Bayes methods, basically what we do is we take the beta parameters in our logistic regression, and before we do any data analysis or modeling, we put what we call prior distributions, which is a statistical distribution saying what we think, absent of any data, what we think those parameters should be. And what's pretty typical in a model like this is, if you think about like the predictors being centered and scaled, we put a really, really wide normal distribution on these parameters, like a standard deviation of 10 and a mean of 0, right? Super, super wide prior distribution. And then what Bayes' rule does is it mixes the prior and the data that you have in your data set to come up with something called the posterior. And the posterior mostly looks like the prior a lot of times when your data is very small or weak. But if you have a lot of data and very, let's say, precise data, then the output of your Bayesian analysis, this posterior distribution, tends to look a lot more like the empirical data that you have. So Bayes' rule is really good at coming up with a mixture of your prior distribution and your observed data to create this thing called a posterior, right? So what we do is when we fit our model in this particular case, and we get predictions like we would from any other logistic regression, like here's the probability that this particular compound is toxic. I keep wanting to say not a hot dog. Thanks, David. So we're going to get like a class probability out of this. And just to remind you, if you remember back from like your old school statistic days when you had to actually look at binomial distributions, that the rate parameter of a binomial distribution has a variance that's, if the rate was p, the variance is p times 1 minus p, right? So just keep that in mind, that relationship there, because we'll come back to it. So one cool thing about Bayesian analysis is, even though my prediction is an actual number, like a probability of it being toxic, what we do is that posterior distribution is actually a distribution around the probability. So we have a probability distribution on a probability estimate, basically. And so what that allows us to do is to get a measure of uncertainty. So if I tell you a compound had a probability of being toxic is like 93.4, plus or minus 0.001, that's a very precise prediction. But if it's much wider than that, we can get that estimate in a Bayesian analysis, which we can't really get in an ordinary logistic regression, easily at least. Okay, so what I did is I used tenfold cross-validation, and the plots I'll show you, the predictions in a minute, are the holdout samples from tenfold cross-validation, right? So I'm not involving a test set or anything right now. And one last little note about this is there are a lot of other models besides like some fancy Bayesian model that you can get these types of interval estimates for predictions. So like there's a recent paper for, let's say, random forest, where it shows how to take a random forest prediction and then get a what we call it's kind of like a confidence interval for the predicted value. So it's not the only way you could have done this. So this plot on the x-axis is the probability of being toxic, and the y-axis is our uncertainty around that prediction, which I've just called a standard error here. So all I did is each one of these data points has a posterior distribution around its prediction. The points here on the x-axis are the mean of that distribution, and the points on the y-axis are the standard deviation of that posterior. So it's sort of like our standard deviation of our predicted value. Okay, and the dotted line going from left to right, that's basically a multiple of p times 1 minus p. And so that gives us a sense of what like our average level of uncertainty is for each of these compounds. And you can see some of them are below the line, which means that they're more precise than what we'd expect on average. But then we have some that are actually pretty flagrantly high, like here and up here. And so one thing about this is, hopefully the color comes across well, is you can see, thankfully, more of our red is to the right of 0.5. That means the model's, working because they're being predicted as a toxic compound. But you see some high flyers here and there. So you see, even when we come down to things that we're very confidently predicting not to be toxic, you see a couple of toxic ones here that have a much higher variation, like up here, than others. So even when you get a very confident prediction, it can have a large amount of uncertainty around it. Okay? So let's take an example. Let's look at something that was predicted to be really, very strong probability to be toxic. We have one that's way up here in terms of its variation. Then I'm going to take one that's sort of in the mass here that has very low variation. Let's look at how does that happen? So let's look at the posterior distribution of those two samples. And so they're both predicted probability of about 0.94, 0.3, 0.4. They come from different folds in cross-validation, although that's not the particular reason that they're different. But if you look at the posteriors over here, what you see is you have this one number 2509 that has a pretty tight distribution around 94.3. And then you see this other one was at 128 that is really confident that it's toxic, except when it's not really, and it feels really moderately confident that it's not toxic. So you have this really polarized bathtub-shaped distribution of your posterior. And it's like a very very bipolar prediction. And so the uncertainty, this is why the uncertainty estimate is so high, because it really does think it's toxic except when it doesn't. And this to me is like a problematic prediction. The variation around this prediction is so high that maybe we don't want to report this one. Right? This would be a reason that we would go back to our chemists and say, yeah, I know what the probability says, but I just don't feel right about this prediction. Let's not use this value. Or in fact, I think we would probably not even give them the probability number. We would just say, yeah, this probability prediction wasn't very good. Right? So how can we label these as being equivocal? Okay, so we need to set up some rules to take the output of our classification model and decide which ones we're going to actually give the consumers of this model, which ones we're not going to. Now, one reason this could happen is extrapolation. So if this compound represented by the blue histograms here was something that was really different from the data that was used in the model, like if you think about your old linear regression class where we showed confidence intervals across a prediction, remember how they sort of flare out at the ends? Right? That's uncertainty, and that's uncertainty due to extrapolation. And my feeling is for this particular example, this compound is very much an extrapolation compared to what was used to build the model, and that's why its posterior distribution is so janky is the technical term. It's not. Don't use that when you're talking to your boss. Yeah, it's really janky. Anyway. So what we're going to do is we're going to come up with basically two rules. The first rule is going to be sort of like I showed at the very beginning, where if we have things that are around 0.5, let's maybe not report them because they're sort of equivocal. We can't really decide if they are, close enough to the line to call it a toxic compound or not. And the other thing we're going to do is we're going to try to find a rule that will flag the compounds that have really high variation, right? But high variation means something different on this end of the scale as it is this end of the scale. So we have to have something that says, for a probability around 0.3, the variation can't be above a certain value. And that value would be different than if the probability was 0.001, okay? So the way I've chosen to solve this here is to come up with basically, a plus or minus around 0.5. And then basically we estimate the standard error, basically using this line here, and come up with a multiplier there. So if you're, let's say, and I just eyeballed this to be honest with you, if you're like about 75% more variable than the average compound, we think that's probably too variable for me to report the actual value. So if you take this plot and apply that rule, we come up with what I on Twitter refer to as the Bucktooth Mustache plot. And that looks like this. All right, so let me explain this. The red line is kind of the rule. So if we have things around plus or minus 0.5, we don't want to report those. So they're above the line. So these would be called equivocal for that level of buffer, right? And then things, down here, these would be reported equivocal, even though they have very strong probability values. The uncertainty is far enough larger than other samples around its value for me to feel safe in making predictions. So then the question is like, well, wait, Max, how did you come up with these numbers? And so these would be basically like tuning parameters for the model, where you want to optimize your equivocal zone such that it gives you a better performance, but not so much that you're excluding almost all predictions. So you probably want to, before you do this, come up with a number that says, we never want to exclude more than 5% of the values that come out of this model, right? So what I'm going to do is I'm going to show you how that works. I'm going to leave the mustache part of this plot alone for a little bit, and then just look at the Bucktooth part. Okay, I'm the same guy who made juice in our function, so take that for what it's worth. But I'm going to see, as we vary the size of the bucktooth here, how that affects performance. So if I start with 0, that means like I'm not excluding anything because there's no buffer around 0.5, and then the numbers on the next plot basically show on the x-axis how wide that part of the equivocal zone is getting and how performance changes. And I use the area under the RC curve to do this. So if you start off with with basically no buffer, but with the mustache part of the equivocal zone, we start off with 100%. So on this panel, it's the number that you report out. So we report out almost 100% of our samples with no additional equivocal zone, and our performance goes immediately from 0.85 to around 0.835 to around 842 or 843. So we get an immediate jump in our performance without losing many samples to being equivocal, and that is simply because that's the ones above the mustache part of the plot. Okay. And so as we increase the width of that bucktooth part, you can see the reportable rate is going down. So around here, we're only reporting about 95% of the results. And then you can see it like linearly decreases, which makes sense. And then you can see performance sort of at a different rate increases in terms of its area under the RC curve, right? And of course, you can keep widening this or not making it wide enough. You would probably choose how wide you want to make it, probably more based on the reportable rate by how many you don't want to make predictions for, than probably the area under the RC curve. Because every time I've done this, I've almost always had a linear increase in performance. So it's not like it really tops out at somewhere. So anyway, this is what I typically see. And again, this is a tuning parameter. So if you wanted to do this, you'd want to have some optimality criterion by saying like, give me the best area under the RC curve under the condition that I always report at least 90% of my data or something like that. Okay. And just so you know, like when I did this in diagnostics, we would actually have a separate R&D trial that collected like 1,000 data points only to do this part of the analysis. Okay, so if you are going to use data to make a decision about what this should be in, either have a separate data set to do it or include it inside of your resampling procedure. All right, so how can you do this? I have a package that I sent to CRAN, and it's not yet approved. It's been about a week, called Parsnip, and that helps with the modeling part here. And then we have a package I hope to put on CRAN before the end of the year called Probably, which I think the sticker is going to be meh. And probably has the bits with the equivocal zone. And so what Parsnip would do is it would enable you to fit this like Bayesian logistic regression or Keras or GlimNet or whatever kind of logistic regression you want to use with a minimal syntax. It's kind of like the unified interface part of Caret, but more tidy. And so if you wanted to do that, you would load the Parsnip package, you tell it you want to do logistic regression, and then the engine is like the package or the computational engine you want to use. So if you wanted to use Stan, you set the computational engine to Stan, and then if there's any Stan-specific criteria or arguments you want to use, you can add them here. So those posterior distributions were based off of, so it did 4 chains, each at 2,000, but you cut out half of them. So it's about 4,000 data points are in those posterior distributions, and those come from me saying the number of chains here, right? And then fit just fits that model, right? So the syntax here is very concise, and it's almost identical if you were using GlimNet or Keras or GLM or whatever code you want to use to fit the logistic regression. And then the little bit to make the equivocal zones here is what we did is the predict method will give you your values. And then what we have is we have a data structure called, I think it's called a class under our pred object, which is basically like a factor. But what it allows you to do is inside the factor, we've marked which elements of that vector should be called equivocal. So it doesn't add like another layer to the factor. It's an additional attribute that we keep along. And when you convert that class pred object to a factor, an actual factor, like when you want to calculate accuracy or whatever, it actually takes all the equivocal values and marks them as NA. Right, so you don't actually, even though they get stored in the data, when you convert it back to a factor to do your analysis, it marks the equivocals as NA. Okay, and if you had an NA going in, that's just one more NA that was maybe not equivocal that gets added to the list of NAs when you convert to a factor, right? So it handles the equivocals in a sensible way and very consistent with what you would do in R. And that also means like if you want to do your analysis on any of these data, you don't have to have like a special like accuracy or precision or recall function to handle these equivocal samples. It just all sort of happens for you. And the syntax you might expect is very dplyr consistent. So yeah, this is all stuff we're building, and hopefully it'll be done by, or at least on CRAN by the end of the year, depending on some other packages that are being released. So in summary, there are times in a model where you don't want to make predictions based not on what the predicted value is itself maybe, but the quality of the prediction. So maybe it's, again, too close to the cutoff, or maybe there's something else about the prediction, like its amount of extrapolation or something like that, that would make you say, yeah, let's not give somebody a number in those instances. And you need to balance, how you make something equivocal. You need to balance the performance and what we call the reportable rate, just to make sure you're not excluding all but the most obvious samples from your model. And then we have packages that are in process for this. Here's a link to the FDA guidance, one of the many FDA guidance that talks about equivocal zones. And here's a link for the paper, and they have their data in a supplemental file, although we have an R package with it. And that is it.